Systems of linear equations in two variables. An ordered pair to a system of equations, that's something like this where we have two equations in two variables. An ordered pair is a solution if it satisfies both equations. So one way to find these solutions is to solve graphically, which means to graph both equations on the same grid and look for the intersection point. In this example, these are already graphed for us. We're just going to observe which is which. This one here is x minus 2y equals 0. I can tell because it passes through the origin. And this other one is 2x plus y equals 5. So the first step here would be to graph both lines using some of our old techniques from sections 1.5 and 1.6, and that's where I would refer you if you're not remembering how to graph lines very well. And then we look for the intersection point, which looks like it's right here at 2, 1, and that ordered pair is also going to be the solution to this system of equations. So 2, 1 is my solution, and the way that I would check that is by plugging it into both equations and verifying that it does in fact solve both, that it does satisfy both equations. So looking first at my 2x plus y equals 5. I would want to plug in 2 for x and 1 for y, and that gives me 4 plus 1 equals 5, and I can tell that yes, that is a true statement. Going then to the second equation, x minus 2y equals 0. Again, I'm going to plug in 2 for x and 1 for y. And I get 2 minus 2 times 1, which is 2, equals 0. And I can see that that equation is satisfied as well. There are 3 different possible ways that this can come out, and one reason that we like the graphing method is that it helps us to visualize what these 3 different cases are. The first one is what we just saw, that the two lines intersect in one point, so we get one solution. The name for this one isn't used very often. It makes more sense after we've talked about the other 2 cases, which are sort of special cases. The name for this one is just saying it is not inconsistent, and therefore it is consistent, and it is not dependent, so therefore it is also independent. Going on to the inconsistent case, this is where we have parallel lines, and as we've seen, parallel lines never intersect. And if they never intersect and the solution is the intersection point, then that means we have no solution. Our third case is where we graph both lines and they turn out to be the same line. So what we have drawn here just looks like one heavy line, but it's supposed to indicate that we graphed 2 lines and they turned out to be exactly the same. That means that every point on that line is also an intersection of the 2 lines because it lies on both lines, and there are infinitely many such points, and that's why we have, in this case, an infinite number of solutions. In elementary algebra, we typically just characterized these by their names and left it at that. We will actually express our solution sets to the dependent systems in this class. There's not a whole lot of extra work in doing that, but it's going to be a slight difference in how we express our final answer. So we're going to express the solution set using set builder notation. We'll see how to do that shortly.